Okay, just as we mentioned, next we will have a look at the application fields and the computing tasks for big data.
Here, we mentioned that big data is leading the future. There is a saying that goes, everything is data and data is everything. This saying reveals the importance of data. We already know that data has assimilated into every inch of the industry and business fields. This is an overview of the application scenarios of enterprise-level big data platforms. As indicated from the overview, big data platforms offer services in many important fields, such as telecom and finance industries, governments, and many other enterprises. Big data platforms have been implemented to process data for operation, management, supervision, and profession, etc. This is a bar chart showing the proportion of big data application in many aspects. In fact, we can tell that big data exists in almost every industry. Here shows some industries using big data. We can see from the picture that big data is most used in marketing analysis, customer analysis, and internal operational management. Just as we mentioned before, retailing enterprises like Amazon or eBay used big data solutions to do marketing and customer analysis for improving their profits, and the users benefit from big data by having better experience. Besides, in each aspect, the proportion of 2019 is always higher than that in 2018, which means that the application of big data is getting more and more attention in industry. Moreover, we can have a look at these two plots. From the left side, we can find that it is predicted that the overall scale of big data industry will exceed China yuan 1 trillion by the end of 2020. And the pie graph on the right is the market scale proportion of big data market segments. In the figure, the red part, which represents the industry solution, accounts for more than 1/4. And after that, the big data application, the basic software, computing and analysis services also play important roles as well, accounting for 15.3%, 12.5%, 12.4% respectively. Next, we can have a look at some cases in detail. The first case is about finance. And here we can have a comparison of the conventional finance and the new finance. In the past, both customers and financial institutions are passive. The customers need to get services in a fixed location and at a fixed time. And they passively receive data as well as propagation from the market information, while the financial institutions like banks could only offer standard industrial services and focus on complicated processes and procedures. But today, things become much better. Now, the new customers can obtain service anytime and anywhere, and they become more active in acquiring meaningful information. As for the new financial institutions, they can use data mining algorithms to analyze the user behavior and thus join user portraits for accurate and personalized advertising and propagation. Next, the education. Big data provides technical support for basic education and higher education. It helps to analyze information, including students' physical activities, learning behavior, exam scores, and career planning throughout their whole adolescent student age. Many of the available teaching data have been stored by government agencies, such as the National Center for Education Statistics in the United States for statistics and analysis. The ultimate goal of big data analytics in the education field is to improve students' learning performance and provide students personalized coaching and learning guidance. Big data is also important in statistics analysis of academic performance. For example, enrollment rate, dropout rate, and the rate of admission into higher schools can be used to promote balanced development of education. And about traffic planning, we can analyze the traffic crowded based on different ages or different ways of getting to some places. Or we can pay more attention to those regions where the traffic load hits a record high. And based on these results, we could make road network planning or bus line planning in order to optimize the city's traffic. And finally, for clean energy, Huawei has made great progress in Qinghai province in China. Qinghai is a place with strong winds throughout the whole year, which means that we can use wind to generate electricity. But in the past several years, the local government hesitated to invest money in wind power because the wind is unstable and difficult to control. Now, thanks to big data technologies, we can make more accurate predictions based on the historical data and have achieved to use wind power for 15 consecutive days. By doing so, coal consumption is reduced by around 800,000 tons, and carbon dioxide emission is reduced by 1.54 million tons consequently. Since then, we can be proud to say intelligent plus data help fight for clear water and blue sky. Okay, next we can have a look at the computing tasks for big data analysis. Generally speaking, there are 3 different kinds of computing tasks. The first type is called I/O-intensive tasks. Here, I/O stands for input and output. And I/O-intensive tasks involves network transmission and intensive reading and writing processes through hard disks or memory. These tasks have the following characteristics. The CPU usage is low, and most latency is caused by I/O weight. During the execution of I/O-intensive tasks, 99% of the time is spent on I/O weight. Therefore, the top priority is to improve the network transmission and read and write efficiency. The second type is the CPU-intensive task, which has the following characteristics. A large number of computing tasks are performed, like pi calculation and HD videos decoding, which consumes CPU resources. CPU-intensive tasks can be completed in parallel. However, more tasks mean longer duration for switching tasks, and task processing on CPU will be less efficient. Hence, to make best use of CPU performance, keep a number of parallel CPU-intensive tasks equal to the number of CPU cores. Unlike CPU-intensive applications, where a single computing task occupies a large number of computing nodes, data-intensive applications have the following characteristics. Firstly, a large number of independent data analysis and processing tasks run on different nodes of a loosely coupled computer cluster system. Secondly, high I/O throughput is required by massive volumes of data. Thirdly, most data-intensive applications have a data flow-driven process. There are some typical applications of data-intensive computing tasks. Please have a look if you are interested. Okay, and here are 4 major computing modes for big data analysis. Firstly, batch processing computing, which is almost equivalent to offline computation. In this case, we can process a large amount of data in batches, but usually we need several hours for data processing. And in the industry, we use MapReduce and Spark to deal with batch processing in most cases. Secondly, stream computing. Unlike the first type, stream processing uses the event-driven idea to process big data, so it could process data in real time. Usually, we use Spark, Storm, and Flink to manage stream processing. Thirdly, graph computing. This is not the same thing as data visualization. In most cases, we use graph computing to analyze the relationship between individuals, and each individual can be regarded as a node, while the relationship can be regarded as the vertices. And there are many famous tools for graph computing, like GraphX, Galley, Giraffe, and PowerGraph, and so on. They can be used to deal with graphs of different properties. And the last one is called query and analytics computing. In big data analysis, we need to manage, query, and analyze data through different storage systems. And the query and analytics computing is like doing computation while querying data simultaneously. This is very much like the OLAP tasks through data warehouses. And for big data, we have tools such as Hive, Impala, Gmail, and Cassandra. This is a graph showing the ecosystem of the open source software framework Hadoop, which is also the main topic of our lectures. Concisely, HDFS serves as the foundation of the whole system, which provides data storage for all the upper layer components. And YARN is a unified resource allocation manager for CPU and RAM resources. Above that, we can see MapReduce, Taz, Spark, Flink, Hive, Mahout, and Pig, all of which are computing engines for different application scenarios. And HBase here is the NoSQL database for real-time data accessing, and Zookeeper is a coordinator who manages the active standby status of the components. Scoop is an ETL tool, and Flume is used for data collection. Woozy is for workflow scheduling, and Embree is for installation and deployment. We will introduce most of the components in detail later, and now you just need to know this architecture as well as the names of the components.
Okay, that's all for this part. Next, we can have a look at the challenges and opportunities faced by enterprises nowadays.